Hey guys, welcome to Pepcoding. Today we are going to learn a really interesting problem, Kosaraju algorithm. This is a algorithm that is asked many times in the interviews. So let's see basically what this algorithm is and how we need to solve it. So let's go to OBS. So suppose I have something 0, 1, 2, 3, 4, 5, 7. This kind of graph is there. Okay, this is my suppose graph. So this is suppose my graph. So guys, in this is a unidirectional graph, directed graph. In bidirectional graph, suppose these are my components, strongly connected components. Why these are strongly connected components? Because from 0 I can go to 1 and from 1 I can come back to 0. But in case of unidirectional graph, I can only come back from 1 or 2 itself when it's a cyclic graph. Okay, see, this is a perfect component, a strongly connected component, because from 0 I can come back to 0 again. From 4 I can come back to 4 again. This is also a strongly connected component. From 8 I cannot come back to 8. So this is not a strongly connected component. Only two components are present here. So guys, if you say that just count the number of cycles and the answer would be here, then I would like to stop you right there, because it would be a wrong answer. Let me show you how. Suppose I have something like this. Okay. Suppose I have something like this. So here we can see that there are total 3 cycles. Okay. This is also my cycle. This is my cycle. This is my cycle. So, but is this a different component? Are these different components? Or let me just say this is also a connection from 0 to 2. So this will also be a cycle. These are not different components, guys. These are one single connected component. Okay. So in this case, we have learned that counting number of cycles won't help. Counting number of cycles won't be helping me. So what I really need to do here is just simply follow an algorithm made by Kosaraju. Kosaraju have discovered this and has come with a solution. See, let me remove this. Okay, what Kosaraju said, that if I simply do the DFS, I can get the cycle. But what about this? This is a problematic edge. I'll say it a problematic edge. This one. So he discovered one great thing that I'll just show you right here. If I discover somehow, I don't know how, but somehow if I am able to discover this problematic edge and then we should do the DFS in this cycle. If I am doing my DFS in this cycle, I cannot come back to here. Let me show you what was happening when I was doing DFS in this cycle. 0 visited, then 1 visited, then I come to 2, then come to 3, and then 4. So here I also go to 4, and then this complete cycle is discovered, and it will not give me the correct output. So what Kosaraju said, that discover this edge. And what if I start, let me just mark them unvisited. Okay, what Kosaraju said was if I put do my DFS in this cycle, okay, in this component from 4 or from any component, say suppose from 4. So 4 visited, then 5 visited, 6 visited, 7 visited, then I can't visit anymore. So I'll backtrack and my count would be 1. Then from 4, I'll back I'll go to here. I'll backtrack to here to 2. Then if I do my DFS in this part, then I'll get another count 2. In this, nothing would happen because cycle won't be detected. So I hope you are understanding this logic that he discovered that if to the endpoint of the matrix, if to the endpoint of the problematic edge, if my DFS is performed first of all, let me just remove this. This is of no need to us. Okay. He said if the DFS is somehow performed first here, then from 4 I cannot come back to 2. But from 2 I was able to go to 4. So this was a problem for me. But now I simply can't. So he discovered this algorithm. This is really special, guys. Let me just show you. This is so amazing thing. What did he said? If somehow I get here, then he found a special logic to get here. First, he said that perform a normal DFS and take a stack. This is my stack. I am at 0. Okay. So let me change my color. So at 0, I marked it true. At 1, I marked it true. 2, I marked it true. Then I went to 3. From 3, I cannot go to anywhere. So I'll add it in stack. Then I backtrack to 2. Then I went to 4, marked it true. 5 true, 6 true, 7 true, backtrack, add 7, can't go anywhere from 7, then can't go anywhere from 6, so add 6, can't go anywhere from backtrack 5, then backtrack 4, backtrack 2, backtrack 1, backtrack 0. So this is my stack. So what did Kosaraju proved it was that at the top of my stack, what I'll get would be a vertex of starting point of the problematic edge. This is my problematic edge, and I would be getting a vertex of the starting point from where I started my DFS in first half. Okay, before the problematic edge, the source point from where the DFS was started would be my answer. I can prove this to you even if I started from 1, then also 1 true, 2 true. From 2, I could go to 3, then to 0. 0 would be in my stack. Then 3 would be in stack. Then from 2, I'll go to 4, 5, 6, 7. All of these will come in stack. Then I'll backtrack to 2, then 1. I started from 1 and I got this. And this would be from the starting in this phase. This is starting and this is end. So in algorithm, my first step was to perform DFS and fill the path in stack. Then what did he said? That if now, after getting this, if we simply transform the edges. So if I simply transform the edges, so now my these edges would be transformed. Nothing would matter to me here, but here it would surely matter because now the point that I have got is here, and now this would be at the end of the problematic edge, not in the chart, because my graph is completely reversed. Okay, so let me show you. The new graph would look like something this. Okay, here also cycle won't be disturbed. It's really obvious that cycle can't be disturbed, as now I would be having, because in circle, no matter that I start from clockwise or anti-clockwise, I'll reach the point again. Okay, cycle won't be disturbed. Now after transposing this, after reversing the edges, if I again perform, see, now I have my source here. If I start performing DFS from this point, then first I'll traverse here, my cycle would be detected here. I can't go to 4 obviously because it's at the end. Then when I'll come to 4, I'll again perform DFS. Again a cycle would be detected. So here, first cycle and this second, I'll get my count and simply I'll return it. So 3 steps: first DFS, second transpose, third normal DFS without stack, and count the number. That would be your answer. So simple. Let's quickly code this. This was Kosaraju algorithm. So first here, yeah. First what I need to do is create a stack. So I am here creating a stack first. Okay, so stack of integer, let's name it s, equals new stack. Sorry guys, my touchpad. The new stack, yeah, a count that would give me the answer to 0. This is of type int. Then what I'll do, I'll simply perform my DFS. Okay, so for performing DFS, we all know we need to make a boolean array visited array. So let's make our boolean visited array. It would be of size n. Okay, now for each loop, so for I int I equals 0, I less than n, I plus plus, if not visited, then in that case perform the DFS. Simple as that. So in DFS, what all I need to pass? I need to pass my list, my visited array, n, and one more thing that I need to pass here is stack. Okay, and stack name is s. Okay, I passed n here. This should be I. Sorry guys. Okay, now what? After getting the DFS in the stack, I'll simply do the transpose. Step 2 was doing transpose. So create a array list of integer transpose. This will get me the transpose. Okay, yep, and this would be equal to, let's call a function transpose, pass my graph in that, here it's list. Okay, and n. So let's make a function transpose public static array list of array list of integer. Transpose, here I'll have array list of integer of, and its name would be list n. This would be my integer. So here what I need to make is a new array list that would be my result. So array list of integer of, and its name would be result. This is new array list. Okay, now what? I'll fill my array list for int I equals 0, I less than n, I plus plus, result dot add new array list of integer. Okay, so guys, I hope I am clear here. Yeah, sorry, this. Now what? For int I equals 0, I less than n, I plus plus. Now for each loop, for integer target, or I could say v, in list dot get I. So basically I'm getting the v of u, and now I'll put it in u of v. So result of I is equal to target. Okay, and finally return the result. Now what? I have performed a DFS here. Need to create a function for the same. So public static void DFS array list of integer lists, comma, what all I was passing here, see, visited array, so boolean visited. Okay, what else? Index I, what else? My stack. So stack of integer s. Okay, now what? Simple DFS. We all know how to perform DFS. So here instead of I, let's check current. That would be much more simpler. Visited of current equals true for integer neighbor in list dot get current if not visited of neighbor, then DFS DFS would be list here, then visited and neighbor as current, and what else? My stack. Now after this I'll simply add it into the stack. So s dot push current return. I don't even need the statement, it's a void type. Finally, after getting the transpose, I need to perform DFS again. So let's copy paste this. But in this, I don't need stack. So remove the stack. The name won't matter to me because arguments are different. Okay, now what? Simply perform DFS again. And before that, make the visited again false. Visited new boolean. Okay, yeah, of size n. Now what? Now simply I'll perform my DFS that I have copied from there. Yes. After every DFS, my count would be plus plus. And simply return my count. Let's check the complete code right here. Okay, here I'm passing transpose. Some mistakes would be there. Okay, no need of for loop. I need to do it while my s dot size is greater than 0. S dot pop okay. What else? Visited I. Okay, count plus plus must be in the if condition here. Okay, now what? I'll return count finally. Else everything seems to be fine here. Okay, DFS is not needed. Okay. Transpose. Yeah, here it should be integer. Anything else? I don't think so. Okay, let's try to run the code. Some error in line 29. $35. 37. 47 list boolean visited int current stack integer s expected this. Okay, right here this same error would come here too. Array list of integer list boolean of visited current. Okay, illegal start of expression. Line 49 integer neighbor in list dot get current. Why it is showing error? It's a simple for loop. Let's see. Okay, here list dot. Okay, same error would be here too. Yeah, it is showing in line 62. Result I equals to, sorry, result of target equals I. Array list integer found. Okay, yes. Dot get target dot add I. Line 68 visited equals true. Okay, here. Okay, finally it is accepted and successful. Let's submit it. So let's quickly code this. So first of all, I need to create a count. That would be 0, a stack of int, a boolean array visited of size n, and all its value should be false. Now for int I equals 0, I less than n, I plus plus, I'll just simply perform a DFS. So if not visited of I, perform DFS, I'll simply pass my graph I visited. Yes. Okay, let's make the DFS function. Void DFS current okay visited and stack. Simply mark the visited of current true, then for int neighbor in current of graph of current, what I need to do is if not visited of neighbor, perform DFS. Pass graph as it is, current would be now neighbor, and visited as it is, stack as it is. Simply after the recursion push, before backtracking, push current. Okay, I hope I am clear. Now I need to transpose. So vector of int trans equals transpose graph comma n. Now what? First this dot clear the visited array, then resize it, then perform another DFS. While the stack is not empty, int current equals s dot top, s dot pop, for int neighbor in graph of current if not visited of neighbor, my bad, I was performing DFS right here, that we need to perform later. So name it DFSS, okay. Graph, why to do the confusion, right? Here would be current, then visited array, that's it. And every time my count would be incremented. Finally I'll return my count. So I need to make now transpose function and DFSS. So for DFSS I won't be working, simply copy paste, remove the stack, change the name, good to go. For transpose, I'm passing graph here, I need to pass trans, my bad. So all good. Now simply write transpose function. This would be same as this, int n Now what? So make a new vector, result. This would be of size n. For int I equals 0, I less than n, I plus plus. For int neighbor, or let's say target, equals graph of I, sorry, in graph of I, not equals. What will I do? I'll simply put my result of I as of target as simple I. So what was this? At ith index I was traveling. Okay, so u in v. Now I'll add at v position the value of u. Okay, so guys, I suppose I am quite clear. Finally I would return my result. Okay, good to go. Error in line 41. Something's wrong. Seems fine to me. This output is coming wrong. Count is not incrementing. Let's see why. This seems fine. This is also fine. Let's see, transpose function looks fine. Let's see the Kosaraju mains function transpose. Okay, here's the catch. I forgot to pass my trans, because that needs to be updated here. Yeah, in trans also the same thing. Copy, paste. Here answer. Let's run now. Okay, it's not. And let's try now. We have made this change here. It's right. Let's submit it. So guys, I hope you liked the video. Please like, share and comment and subscribe to Pepcoding. Thanks for watching.